Hello, water managers. My name is Matt Fleming. I'm part of the Water Management Systems Division at the Hydrologic Engineering Center, and this is the third video in the HEC-HMS Real-Time Hydrologic Modeling series. And in this video, we're going to focus on the HEC-HMS Basin model. All right, and so some of the topics that we're going to cover, so discretization, the snow method that you will probably use if you need to use a snow method, the loss rate, transform, base flow rerouting, and reservoir options that you should really consider for real-time forecasting. On this slide, you see a figure of a typical HEC-HMS basin model. What you see here is lots of subbasins represented with these polygons. There's a reach network. You can see how the subbasins and reaches and junctions are connected to one another. Those locations or those junctions that have the red square around them, what those are computational points. So the modeler that created this basin model, what they did is they identified those locations as locations with observed flow. And then whenever you open the basin model map, that's what you see on this figure, you'll see those locations with observed flow identified with those red squares. One thing that I really like when I saw this basin model or this HMS project is there are separate basin models for different conditions in the watershed. For example, in this project, there's a dry basin model and a wet basin model. And what that tells me is there are parameter values that have been somewhat calibrated to certain conditions in the watershed. Right, you would expect different soil moisture conditions if you began a simulation under dry conditions versus beginning a simulation under wet conditions. So having these different basin models with these different parameter sets, they're going to allow you to get to a calibrated basin model much more quickly versus having just one basin model and then adjusting those parameters every time you create a forecast. So if you do have a set of basin models tuned to different conditions, those are going to help you whenever you create a new forecast. You can select the basin model or those conditions that best reflect the condition in the watershed at the time that you create the forecast. All right, the first topic we'll go through is discretization. And what I think of when I think of discretization is the smallest element that you have the software, the program compute results for. And in this example, we have the largest type of element, the subbasin level. And if you use just subbasin average discretization, what that means is you're asking the program to compute subbasin average precipitation, and then you're doing the loss computations, the unit hydrograph, base flow, and all of those computations at the subbasin level. Most SWMS models are going to use some kind of smaller grid scale discretization. And you can see the figures on this slide. We have 2,000 meter discretization for this basin, and then a 5,000 meter grid discretization. So with this gridded discretization, what that means is gridded precipitation is being applied to the model, and then your loss computations are being performed at each of these grid cells. And then the transform, most models are using the Mod-Clark transform, that unit hydrograph is being applied on a distributed basis across each of these subbasins. This finer discretization really comes in handy if you have spatially varying precipitation. If spatially varying precipitation within the subbasin really doesn't happen, then you should really consider using larger grid cells. So experiment with a 5,000 meter grid cell, or you could also experiment with not using grid cells at all. You don't have to use the Mod-Clark transform method. You could use the Clark transform method, and then more or less, if you're using just the Clark transform method, then the subbasin average discretization is really what you're using. So bottom line, experiment with different discretizations, because if you do have a lot of subbasins, you're already capturing the spatial variability of precipitation, and it might not warrant going to a 2,000 meter grid. All right, let's jump into the snowmelt topic. So if you do have a watershed in a colder climate and you need to use temperature index snow, there's a few key parameters that you should really understand. The first one being is the initial snow state that you set the snowpack at the very beginning of the simulation. There are 5 state grids that you need to define for SWE, or for this temperature index method. You could just set the other method, the other variables, so your initial cold content, initial liquid, cold content ATI, and melt ATI. You can choose just the default values, and what that means is you're assuming a ripe snowpack. The snowpack is ready to melt if you choose the default values. And then your initial SWE grid, there are products available from Cumulus that you could set up in your extract list to download, and then use that grid to initialize the snow water equivalent, how much snow, how much liquid water is available in the snowpack at the very beginning of the simulation. Okay, so you do need to configure your initial SWE because you have to set that initial SWE correctly at the very beginning of every simulation. The next parameter to really understand is the PX temperature. The PX temperature, what that means is this is the temperature that differentiates liquid precipitation versus frozen precipitation. In this example, the PX temperature is set to 32 degrees Fahrenheit. And so if the temperature was 33 degrees and it was precipitating, then that precipitation would be falling as liquid rain. If the air temperature was 31 degrees, then the precipitation would be falling as frozen. The wet melt rate is used to identify melt when the precipitation, liquid precipitation, is falling on the snowpack, and that precipitation rate has exceeded a user-defined value. So for example, in this figure, the rain rate limit is 1 inch per day. If the rain intensity is greater than 1 inch per day, and it's still precipitating, then the current snowpack is going to melt at this wet melt rate. So this is a parameter that you can fine-tune during a calibration because it is variable given the time of year and the snowpack conditions. All right, let's jump into simple canopy and deficit and constant. Most SWMS models are using simple canopy and deficit and constant, and the way that I think about these two options are they're simple tanks, right? So canopy storage is represented by a layer, some kind of storage depth, and then the soil is represented by one layer as well. I like to simplify this. I like to set my maximum canopy storage to 0 inches just because I consider all losses coming from the loss method, my deficit and constant, my initial deficit here. And so really, it's okay to have 0 canopy storage. The canopy is still going to remove moisture from the soil during those periods of no precipitation. So this is usually how I configure the canopy method. And then for my soil layer, again, the two parameters that really represent that storage, your initial deficit, so how dry or wet is the storage, the soil layer at the beginning of a simulation, and then the maximum deficit is how dry can it get during extended periods of no precipitation. More than likely, you're never touching the maximum deficit. It's probably been set based on some historical calibration that you've performed. That initial deficit, this is a parameter that you really need to understand or define that reflects the conditions of the watershed at the very beginning of the simulation. And then the other really important parameter, the constant loss rate, this is how saturated or how, when the soil is saturated, this is that rate, that percolation rate that water moves through the soil. Okay, so once the soil has been saturated, water is going to infiltrate into the soil, and you notice this one arrow coming out of the soil layer. It's percolation to a deep aquifer or base flow. If you do link the linear reservoir base flow method with the deficit and constant method, then you do get mass balance. The water that infiltrates when the soil layer is saturated does go to the base flow layer. Let's talk about transform for a second. So you're very familiar, I'm sure, with the unit hydrographs and what that really means. And the Maud-Clark method, so most SWMS models probably have the Maud-Clark method used. And that method has two parameters, time of concentration and the storage coefficient. Time of concentration means how long does it take for water that falls in the most remote portions of the watershed to run off the watershed. And the storage coefficient, this is really a calibration parameter. It reflects the natural attenuation of the watershed. So a watershed that's able to store water and release it more slowly, it's going to have a large storage coefficient versus a watershed that water just flows off the watershed very quickly. So with the Maud-Clark method, I really think of it as a distributed unit hydrograph approach. The program is computing unit hydrographs for each of these subbasins as water is routed from that grid cell to the outlet. Water is not routed from grid cell to grid cell, it's from the grid cell to the outlet. You can experiment. You can see if your run times drastically decrease by switching from Mod Clark to Clark. So just give that a try. There are some options in HMS though to account for different conditions in the watershed. There's also a variable Clark and a variable Mod Clark method. And what that means is you can define a relationship between these parameters, time of concentration and storage coefficient, and your precipitation intensity. Right? And what you should expect, or what we've witnessed in nature, is as those precipitation intensities are increasing, as you have more and more depth of water on your watershed, velocity should increase and the natural storage should decrease. And you can set up relationships that reflect that so that as your storms intensify or as that precipitation rate intensifies, you can reflect or model that quicker responding watershed. All right, the next topic, base flow. Most SWMS watersheds probably have the recession base flow method defined. This is a pretty simple method. It does not conserve mass, so you have to watch out for this one. The one parameter, initial discharge, this is the base flow at the very beginning of the simulation. That recession constant, this is a parameter that impacts the shape of this recession curve, right? So if it's a value of 1, then you have a horizontal line. There is no base flow recession if the recession constant is 1. If you have a recession constant that's very close to 0, then you're going to have a quick responding or quick recession to the base flow curve. Okay, so you can experiment with different recession constants. And then the ratio to peak is when does that base flow curve turn on? And the ratio option is selected here. A value of 0.1 means when the ratio of the peak flow to the current flow is less than this ratio to peak of 0.1, then that base flow curve turns on. So in my example, if I have 100 CFS as my peak flow, my ratio is set to 0.1, then my recession base flow curve turns on when my recession limb of my direct runoff hydrograph gets to 10 CFS. So it's a very simple method, but you have to be careful because if you have different combinations of the recession constant and ratio to peak, then you can actually add mass or add volume to your runoff hydrograph. The base flow method that I really suggest folks consider is the linear reservoir base flow method. And the reason why is this one does take input from your soil infiltration method. So that constant loss rate, when the watershed is saturated, that infiltration or that percolated water is distributed down to the linear reservoir base flow layer. And then you can control how much water goes into the groundwater 1 layer and the groundwater 2 layer. In my example here, I have 10% or 0.1, 10% of the infiltrated water going into my groundwater 1 layer and 35% going into the groundwater 2 layer. These fractions don't have to add up to 1, but they cannot exceed 1. You cannot add volume to the base flow hydrograph. Okay, so this is what I found is this is very much a calibration parameter, but once you define what the fraction is for a watershed, it's pretty consistent for the different conditions. Right, for saturated conditions or watersheds that are somewhat saturated, those groundwater fractions are going to be pretty similar from event to event. And then events that happen when the watershed is relatively dry, those groundwater fractions are going to be fairly consistent from event to event. Your groundwater 1 coefficient and groundwater 2 coefficient, these are very similar to the Clark storage coefficient. And so what I do is I usually tell folks, hey, just go ahead and set the groundwater 1 coefficient to exactly equal your Clark storage coefficient, and then set the number of groundwater 1 reservoirs in series to 3, 4, or 5. And you can set that through calibrating the model to a couple of historical events. And then for your slower responding base flow recession, you're going to have a really high groundwater 2 coefficient. And I usually start out with a value that's 100 times larger than your Clark storage coefficient, and then set the number of linear reservoirs for groundwater 2 to 2, 3, or 4. If you just experiment through a couple of simulations, you can get a really good idea what this linear reservoir in series the number of reservoirs, how that impacts the shape of your groundwater response. So in my example here, I'm using the groundwater 1 layer to simulate interflow. So water infiltrates into the soil, and then it flows back onto the land surface and then flows to the channel network, so that's your interflow. And then the base flow is water that infiltrates into the soil and stays much longer in the soil, and then finally pops back up into the land surface and flows to the outlet of a subbasin element. So you can model both of these groundwater contributions with groundwater 1 and groundwater 2. All right, moving to the reach routing methods. More than likely, you do not have to modify these parameters when creating a forecast and calibrating the model. These are the typical methods that most SWMS models use. You have the variable lag and K, modified poles, Muskingum and Muskingum-Kunj. One thing to watch out for, though, is with the Muskingum method, it's a static relationship between lag and attenuation. And so if you're modeling events that are much larger than those that the model was calibrated to, then you probably do need to adjust that lag parameter. You probably have higher velocities. That's why I really promote the variable lag and K method, because with this method, you can set a relationship between flow rate, the lag, or attenuation, and that with lag, the time lag, and then K, the attenuation factor. And then modified poles, most watersheds have those if they have RAS models, right? Those RAS models were usually defined or used to help define those modified poles relationships for HMS reaches. And then the Muskingum method, the only thing I really have to say about that one, it is computationally burdensome. And so I've seen a lot of watersheds or models where there's really short reaches, less than 5 miles of reach length, and I would really suggest for those really short reaches, you could probably set the reach routing to none and get away with no routing in those reaches, unless that reach is really flat. So do a little investigation, check the routing for some of your reaches. If you see very little attenuation and lag, then you could probably set that reach to none routing, and you'll see a time saving in the computation. All right, reservoirs. So with your reservoir elements, you can choose different options for reservoir routing. I'd say most SWMS watersheds are using the outflow structures option. And with the outflow structures option, they probably have the release set to yes. And what that means is you can choose a discharge gauge and set that as the outflow for that reservoir element. And then HMS will take that discharge time series as the outflow and then take the inflow that's computed by the program plus the elevation area, elevation storage information that you've defined, and compute the reservoir elevation for you. So you can compare the observed elevation to the computed elevation. You can also specify evaporation from the reservoir. So there's an option here on the left side for evaporation. Once you set that to yes, then you can define the monthly rate. All right, that's all I have for the Basin model. If you have any questions, these are additional resources that you can take a look at, and thank you for your time.